Good day, I'm Norman Wildberger. In our last video, we introduced this idea of a core circle as an alternative to the unit circle. So the core circle is this circle right here, whose diameter is the interval 0 to 1. It's centered at the point 1/2, 0. And today we're going to see that this core circle naturally lends itself to a very pleasant protractor, which I'm going to call Paul Miller's protractor, in honor of a retired engineer in the UK who discovered this particular way of thinking about measuring spreads, or, in our context, projective quadrances. So the story is this. So let me remind you of the basic setup. Here's our core circle. Here's a particular line through the origin, what we often call a projective one point, from the projective point of view where we're only looking at things from the origin. So this line, say, passes through the point UT, and if we normalize it appropriately to get the point u squared over u squared plus t squared, ut over u squared plus t squared, then that's a point on the core circle and provides a one-to-one correspondence between lines through the origin and points on this core circle. This is a complete and precise and total correspondence, a way of really visualizing the projective line as a circle in our familiar two-dimensional affine plane. In particular, the line that passes through the origin and is vertical is associated to this point here. Okay, we're going to see that this correspondence also allows us to visualize what a projective quadrant is very directly. All right, so we have this point A here, just on the core circle, and we could, say, drop a perpendicular down to our diameter. And then we would get a point on the x-axis there, whose coordinate is, of course, just this x-coordinate here, u squared over u squared plus t squared. So this diagram shows how a circle with diameter 0, 1 can be used to effectively measure spreads or projective quadrances. And the reason is that this number, this x-coordinate, let's call it s momentarily, turns out to be also the spread between this line and this line, or in our earlier context, the projective quadrants between this one point and this one point. It also turns out to be the spread or projective quadrants between this line and this line. So this spread here, in the context of two-dimensional rational trigonometry, or this spread here, they're the same. They are both read off as being the x-coordinate s that appears here. Moreover, the quadrants between here and here is also s. So the same diagram measures two spreads, one here, and quadrants, and allows us to read that off just by looking at the projection down of a point on the core circle. This is a beautiful way of visualizing and interpreting and measuring spreads. So let me clarify the notation that we're using here. So we're using these two words, projective quadrants and spread, somewhat interchangeably. They are actually somewhat different concepts, although they turn out to be effectively the same. So the projective quadrants is a term that arises in one-dimensional projective geometry, where we're only considering projective one points, or lines through the origin. The spread is a measurement that arises in two-dimensional affine geometry, once we have a Euclidean structure. And it turns out that the same formula really defines the projective quadrants and the spread. But let me just clarify what the actual official definition is of a spread between two lines in the affine setting. So if lines L1 and L2 have direction vectors V1, which is the vector x1, y1, and V2, which is the direction vector x2, y2, then the spread between these two lines, L1 and L2, denoted by S, is, well, it's given by exactly the same kind of formula that define the projective quadrants. x1, y2 minus x2, y1 squared in the numerator divided by x1 squared plus y1 squared times x2 squared plus y2 squared. And we can rewrite that as a similar kind of expression with a 1 minus and now a dot product squared in the numerator. x1, x2 plus y1, y2 squared over the same denominator, x1 squared plus y1 squared, x2 squared plus y2 squared. So in the case when the two lines are actually going through the origin, then these direction vectors are really the same as our projective coordinates for those lines. And so the spread agrees exactly with the projective quadrants that we defined earlier. But strictly speaking, projective quadrants arises only in the one-dimensional projective setting so far, while this is now a metrical definition that works for any two lines in the affine situation. Now this is a fundamental concept in rational trigonometry, and it replaces the notion of an angle. It's a rational equivalent or analog of an angle, but it's algebraically much simpler to work with, it's easier to compute, and it generalizes in a much nicer fashion in all kinds of other settings. You can learn more about spreads by having a look at the original series on this channel, which is Wild Trig, going back a few years now. But also my Universal Hyperbolic Geometry series. Somewhere around between videos 30 and 40, I start talking about rational trigonometry, and there you can also have this subject laid out for you in a somewhat different way than I'm doing it here. Okay, so very fundamental concept, and we'd like to know, how do we measure a spread between two lines in practice? So in mathematics, if we have a fundamental concept, we want to be able to exhibit examples that illustrate that concept. And we want to be able to make computations that illustrate the concept. Examples and computations are the sort of core underpinnings of mathematical theories. So let's have a look at how we can measure some spreads in a very concrete example. Here's a triangle in the affine two-dimensional plane. A1 is the point -1, -2. A2 is the point 4, 1. A3 is the point 1, 3. Forming a triangle. There are these three lines, the sides of the triangle. And so there will be three spreads, one here, and one here. So let's have a look at this spread S1 here, which is the spread between this line and this line. Well, we need direction vectors. So the vector from A1 to A2 is 5, 3. To go 5 over and 3 up. In other words, you take the difference in the x-coordinates and you take the difference in the y-coordinates. A2, A3, this vector here, is -3, 2, over 3 and up 2. And from A1 to A3 is vector 2, 5. So these are the vectors that we're going to use to calculate the spreads. So the first spread S1 is the spread between A1, A2 and A1, A3. So it's these two numbers that we're going to use, and it's the same formula that we've been using all along for the projective quadrants. So 5 times 5 minus 3 times 2, all squared, divided by 5 squared plus 3 squared, times 2 squared plus 5 squared, for a total of 361 over 986, which you can check. Similarly, S2, spread between these two lines. So we're talking about the vectors A2, A3, and A1, A2. And it doesn't matter whether we use that vector or a multiple of it or it's negative, because the expression is homogeneous. So whatever multiple you introduce in the numerator, it gets cancelled out with the corresponding thing in the denominator. Alright, so you can check that with these two, you get a 5 times 2 minus 3 times minus 3, all squared, over the sum of squares here, times the sum of squares here, and we get 361 over 442. And finally, the spread S3 up here is, well, you can check, you get 361 over 377. Now I'd like to impress upon you, all right, the fact that we are getting concrete, explicit answers, first of all, that in fact we don't really need a calculator, we can do it by hand easily enough in this situation, and that the corresponding problem for angles is essentially unsoluble. If I asked a student in mathematics to calculate for me the three corresponding angles of this exact same triangle, it would be highly problematic. They would, well, they could first of all get a protractor and find some approximate values, that's fair enough. But if they wanted to get exact values for the angles, they would have to do some dot products or make some determinants, and eventually they'd have to feed that into a calculator to calculate some inverse cosine function or inverse tan function or something or other. And the calculator would give them an answer to a certain number of decimals, and they would give us this answer to a certain number of decimals. But that answer to a certain number of decimals is not really correct because it forgets about all the remaining decimals that have been truncated by the calculator. It's just a fact of life that you get used to if you're a mathematics student, that whenever you're asked about angles in a triangle like this, of course it's an approximate subject. You can only ever give approximate answers. So it's a real turnaround in your thinking to start thinking, well, wait a minute, with this approach we can nail down this measurement exactly. We don't have to resort to approximations, to truncations. We know exactly what these three spreads are. This is 100% correct arithmetic. We can apply the same standards of correctness and rigor to geometry as we're used to in arithmetic. One is not less than the other. Another interesting observation is that the 361 is appearing here. And if you think about it, that's not really a surprise because you probably know by now that this numerator is really measuring a determinant, which is pretty close to being the area squared of this triangle. Okay? And whether you measure it from here or from here or from here, you're getting the same quantity. So I hope that's not too much of a surprise, although it's an interesting observation. And now an exercise for you. Check that these three numbers, S1, S2, and S3, satisfy the projective triple quad formula. In other words, that if we plug them into the spread function, then we get 0. And let me remind you what that means is that you take S1 plus S2 plus S3 squared, you subtract 2 times S1 squared plus S2 squared plus S3 squared, and you subtract 4 times the product S1, S2, S3. So the difference between the left and right-hand sides of the triple quad formula, the projective triple quad formula. Okay, and you might like to think about why this is. Is this some kind of miracle? Well, it's really not much of a miracle if you've understood the projective triple quad formula in the one-dimensional case. This is really very similar to the one-dimensional case, even though it's appearing in 2 dimensions here. And the reason is because if we take one of these lines and we move it, then the spreads stay unchanged. In particular, if we move that line so it's meeting at the same place where these other 2 lines meet, then we get 3 spreads which are all at the same point, and then it really is basically the projective triple quad formula. So please think about that. That's an interesting point. This fundamental relation is now booting up from the one-dimensional projective case to suddenly telling us a fundamental fact about the geometry of a triangle in our Euclidean 2-dimensional space. Very, very fundamental formula. Okay, so now I would like to establish the various claims that we made with Paul Miller's protractor. So here again is the basic situation. We have our core circle. We have a point on it called A. It's on this line through the origin, through some point U, T. So in fact, we know that this point A is actually given by this expression, what we call C of ut. U squared over U squared plus T squared ut over u squared plus t squared. We have a few other points around. The origin O is 0, 0, B is the point 1, 0, D up here is the point 0, 1, and this projection down onto the x-axis, we'll call that S0, and that's of course u squared over u squared plus t squared 0, just taking the x-coordinate of the point A and putting it there, and 0 for the y-coordinate. So we're defining S to be equal to u squared over u squared plus t squared. That's S. Okay, so the first order of business is to compute this quadrance here. This quadrance between O and A. Well, that's simple. We're just taking the sum of the squares of the entries here. So this thing squared plus this thing squared. And now there's a common factor of u squared plus t squared squared. There's also a u squared that appears here and also here. So if we take the u squared out, we'll get also u squared plus t squared. And that u squared plus t squared factor on the top will cancel with one of them on the bottom, leaving just u squared over u squared plus t squared, which is S. So this quadrance right here is also S. Already this is a very useful aspect of this core circle. That if you want to measure a quadrance between here and any point on the circle, all what you do is you just drop down a perpendicular and you measure that x-coordinate. And it's always between 0 and 1. So very simple. So if you have this segment here, for example, and you want to know what's the quadrance, you don't have to take your ruler and measure its length and then square it. You just take that point and you drop it down and you measure that x-coordinate, and that is the quadrance. It's actually simpler than the distance. If I ask you what's the distance from here to here, well, you have to take your ruler and you have to make that measurement. Here you just drop that thing down and there's an x-coordinate on this ruled line right here, you just read it off. Okay, next order of business, the spread between OA and OD. All right, well, what are we going to do here? This is a line with coordinate UT. This is a line with coordinate 0, 1. So basically taking the projective quadrants between 0, 1 and UT. And so it's U minus 0 all squared over u squared plus t squared. Or if we did it between 0, 1 and A, we would get this expression. But actually it's simpler if we just look at it as the line UT and the line 0, 1, and the projective quadrants between them is u squared over u squared plus t squared, which again is S. So we can say that this spread here, which I'll write like this, is S. The value of this spread is exactly the same as this coordinate here. So for example, if you want to measure spreads, you take one line, put it there, you take the other line there, you move it over here, see where it meets the core circle, read off the x-coordinate, that is the spread. Very simple. The other spread we're interested in is the one between OB and AB, this one right here. All right, so that's a projective quadrants or spread between 1, 0, direction vector for that one, and okay, between here and here we have to take the difference between A and 1, 0. Okay, let's have a look at what that is. So if we take this thing and we subtract 1, then if you imagine taking this and subtracting 1, the u squareds will cancel and we'll have a minus t squared up on top. This will just be the same. So it's the projective quadrants between this line and this line. And so the formula is this times this minus this times this, all squared, divided by this squared plus this squared, which is 1, and this squared plus this squared. All right, so then this down here simplifies. There is a common factor of t squared, and there's a u squared plus t squared, which will cancel with one of the u squareds plus t squareds in the denominator to give us t squared over u squared plus t squared in the denominator. And then when we simplify, that, we get u squared over u squared plus t squared. One of the u squared plus t squareds here will cancel with that one, and the t squared here and the t squared there will cancel. We're just left with this expression, which again is s. So this spread is also s. All right, so this is the essence of Paul Miller's protractor. Okay? The fact that this diagram involving the core circle allows us to simultaneously measure a quadrant and a spread from the vertical line and also a spread from the horizontal line just by dropping down perpendicularly to the x-axis and measuring off the x-coordinate, which is necessarily between 0 and 1. Notice in particular that we don't need to have the circle itself subdivided in any fashion. An ordinary protractor, such as this one here, okay, that requires careful subdivision of the circle, 10, 20, 30, 40, you're dividing the circular measure up uniformly according to some pattern. That's actually rather challenging to do accurately. Notice we are not requiring that here. Here it's much more elementary. We're just taking a point on the circle, so we're using the circle itself, and then just dropping a perpendicular to read against this linear scale. So this way of looking at things, you see that the spread is actually a more elementary, easy to understand concept than an angle in some ways. Computationally, it's easier to make a protractor like this than it is to make a protractor like this. So, Paul Miller's spread protractor is simpler than a usual protractor for measuring angles because it requires only a linear scale from 0 to 1 along a diagonal or diameter, and some rulings to project vertically. So, to measure a spread, okay, one way of measuring a spread, let's say you have two lines meeting somewhere, then you line up one line with diameter OB, and you pass the other line through B. So let's say the other line is, they say something like that. So we're having one line here and one line there. You put your core circle there so that this diameter is aligned with one line, and then the other line passes through B. And then the spread is this diameter coordinate. So you see where this second line meets the core circle, and you project down. Okay, and whatever that value is there on your linear scale, that is the spread. Here I've subdivided the circle into eighths. Turns out to be actually somewhat interesting to have a scale where 1/2 is important, of course, but also 1/4 and 3/4, because they correspond to the usual angles of 30 degrees and 60 degrees. So 30 degrees is like exactly the same as a spread of 1/4, and 60 degrees is exactly the same as a spread of 3/4. So those three numbers, 1/4, 1/2, and 3/4, sort of play an important role. They capture these angles, 30 degrees, 45 degrees, and 60 degrees, which 95% of classical trigonometry always uses. Because classical trigonometry can't deal very easily with other angles. Here, we are much more flexible. There's nothing dramatically special about those particular values. We can measure all kinds of spreads and get all kinds of numbers and examine all kinds of different triangles. Much more flexible and powerful. So this is one way of using the core circle. We're measuring a spread which ends up being at the point B, at the point 1 over here. So we're measuring the spread between this line and this line, and you just position the core circle as you like, and then you just read off the spread. Very simple. So there's a second method. We could use the other formula that we derived to measure a spread. So we could line up one of the lines with the tangent OD rather than the diameter, and pass the other line through O. So we could be in a situation where we have, say, two lines like this. One of them being that line, the other one being that line. Then what we do is we do the same thing. We see where this point meets the core circle, drop down, measure that linear coordinate, in that case 3/4, and then we can deduce that this spread there between the tangent and that line there is S. So in this case, that will be 3/4. We've just found ourselves a spread of 60 degrees. Now there's a variant on this story which I might mention, that we've been talking about this core circle which extends in the x direction. One could also consider the y core circle, say with the equation x squared plus y squared equals y, which is similarly positioned above the x-axis in the y direction from 0 to 1. And then one could use the same kind of idea. You can check that if you have a line through UT, then its intersection with this y core circle is the point UT over u squared plus t squared over u squared plus t squared. Same kind of thing as we've been talking about, basically just interchanging x and y coordinates. And now if you wanted to measure spread, you could use this approach with this situation in probably a more traditional fashion, in that one line is horizontal, the other line is emanating from the origin now. So if we want to measure that spread, we could use this setup to see where this line meets this y core circle, go over to the y-axis and read off whatever coordinate we have there for this spread S. Right. So very easy way of visualizing what a spread between two lines is, either here or here, same. So we're learning that this core circle is actually a very useful tool in geometry, this circle right here. And I'd like to now show you that in fact it gives us some additional important insight into the algebraic structure on the projective line that we talked about earlier. It gives us in fact a very geometrical way of understanding this algebraic structure. So here's the theorem. The theorem is that suppose that A1, A2, A3 are projective 1 points, with the property that A1, A2 equals A3. So that this times this equals this. Now this is in the context of that multiplication of projective 1 points that we defined when we're talking about rotations. It's basically the same as complex number multiplication. So you can think about it just taking 1 point on one of the lines, another point on one of the other lines, taking the complex number product and seeing what line that product lies on. Let's also define A0 to be this line 1 to 0. So if C0, C1, C2, and C3 are the corresponding points on the core circle, so C0 there, C1 there, C2 there, C3 there, then the statement is that C0, C3, this line here, is parallel to the line C1, C2. In other words, we could determine this point C3 purely from the geometry of the circle by just connecting C1 and C2, drawing a parallel line to that through C0, or the point 1, and wherever that line meets the circle, that is automatically C3. This is a geometrical way of understanding the product of these projective 1 points. Okay, so for example, if A1 is 3 to 1, as in the example here, and A2 is say 1 to 1, then the product, A3, is determined by, and here's the formula, 3 times 1 minus 1 times 1, 2, 3 times this one plus 1 times this one, for a total of 2 to 4, or 1 to 2. So 1 to 2, there's the product. So now in this case, the corresponding points on the core circle are C1, obtained from here by taking both coordinates and multiplying them by the x-coordinate and dividing by the quadrants, which is 10. So if we multiply by 3 tenths, we get 9 tenths and 3 tenths. Here we have to multiply by 1 over 2, giving us 1/2, 1/2. And for A3, 1 to 2, we have to multiply by 1/5, giving us 1/5, 2/5. And the claim is that, well, this vector here is parallel to this vector. So the vector C1, C2, joining these points, so we have to take the difference of coordinates. So 1/2 minus 9/10, that's 5/10 minus 9/10, that's minus 4/10. 1/2 minus 3/10, that's 5/10 minus 3/10, or 2/10. While C0, C3, to take the difference between C3 and 1, 0, will be 1/5 minus 1, which is minus 4/5, and 2/5. Claim is these are parallel. And are they? Well, yes, this one's just half of this one. This happens to be exactly half of this one, pleasantly. So in this example, yes, we can see that this works. The theorem says it always works. So this is an interesting algebraic structure on a circle, which actually I talk about more generally in one of my earlier algebraic topology videos. I think number 2 or 3 or 4. There's one entitled Algebraic Structure on a Circle, or maybe a conic. So you can have a look at that where I talk a little bit more about this structure. So what's the proof? Why is it true? All right, so let's have a look at the proof. It's just a computation, introducing coordinates and doing the obvious thing. So we let A1 be the projective 1 point U1 to T1. We let A2 be the projective 1 point U2 to T2. And we remind ourselves that the product of these is obtained by taking U1, U2 minus T1, T2 to U1, T2 plus U2, T1. So a familiar complex number kind of multiplication applied to projective 1 points. Okay, the corresponding points on the core circle, there they are there. We've seen that several times already. There's the C1 and there's the C2. So to find the vector joining these, we have to take the difference between the coordinates. And that difference will involve a common factor of this denominator, U1 squared plus T1 squared, U2 squared plus T2 squared. We're going to have to get that common denominator, so let's take it already outside just to begin with. And then we have to take this thing times this one minus this one times this one in our first coordinate, and correspondingly this times the denominator here minus this times the denominator here in the second coordinate. Okay, and then we expand this all out. There's a bit of cancellation here. This U2 squared, U1 squared, and the U1 squared, U2 squared there cancel out. We just end up having two terms left over here. And then I've just expanded these terms out there. And I've introduced Q1 and Q2 for these two factors, just to make things a little bit simpler. And then one observes that this quantity here is actually the product of U1 T2 minus U2 T1 times U1 U2 minus T1 T2. Right, so this one times this one is that term. This one times this one is that term. This one times this one is that term. And this one times this one is that term. All right, this is a difference of squares, so it has also a factor U2 T1 minus U1 T2, which we can pull out with a minus sign. So we'll pull out this U1 T2 minus U2 T1 with a minus sign, and then the other difference of squares factor is that one there. And after we've taken this thing out with a minus sign, we're left with negative of this. So that's an expression for the vector from C1 to C2. Okay, so now let's have a look at the third point, A3, which is the product of these A1s and A2s. And it's given by U1 U2 minus T1 T2 to U1 T2 plus U2 T1. That's basically our complex multiplication looked at projectively. Now, the sum of the squares of these two things is a familiar identity. That's important for us because when we form the associated point C3, we have this sum of squares in the denominator. And this sum of squares is exactly Q1, Q2, the product that we were just talking about. So the associated point C3 is this first coordinate squared over Q1, Q2, and then the product of these two over Q1, Q2. Now the other point we need is the point 1, which we might call C0. That's the point 1, 0. And so we want to find the vector joining this point to this point. So we take the difference between these coordinates and write it as a vector. All right, let's take this common denominator out as a factor, 1 over Q1, Q2. And then we'll have this still there. And the minus 1 which appears, because we're taking the difference there, becomes a minus Q1, Q2, because we've taken that factor Q1, Q2 out. And this numerator is still there. All right, now if we take this thing here and we subtract Q1, Q2, from this expression up here, this thing minus Q1, Q2 is just negative of U1, T2 plus U2, T1 squared. And then when we look at these two terms, we see that there's a common factor of U1, T2 plus U2, T1 appearing in both factors. So we can take that out along with this minus sign that's there, giving us just a single U1, T2 plus U2, T1. And then this will have to be multiplied by minus 1 because we're taking out minus this factor. And now we see finally that this thing is almost the same as what we found the vector C1, C2 to be. In fact, we see that if we take C1, C2 expression and multiply it by U1, T2 plus U2, T1, then we get the same thing that we get when we take this expression and multiply it by U1, T2 minus U2, T1. So we find that not only, in fact, are these two vectors parallel, but we can see exactly what the ratios of those vectors are given by these two particular expressions, becoming sort of familiar expressions to us. So this proves the theorem that the algebraic structure on our projective line, interpreted as an algebraic structure on our core circle, has this very simple geometrical prescription just involving drawing parallel lines and this point C0, the identity. It's a very beautiful and practical manifestation of this algebraic structure. So the geometry, the algebra coming together. In our next video, I want to put all these things together and go full circle back to the relativistic addition of velocities and show you that this core circle thinking, this idea of applying Paul Miller's protractor to understand what spreads are, this geometrical connection between algebraic structure and geometrical structure, that all happens in the relativistic setting as well. There's a beautiful uniformity to what's going on here. The same insights that we've obtained here can be applied almost directly to the relativistic situation. And I'm hoping that even physicists watching who have studied relativity for a long time will see some aspects of their subject in a new light in our next video. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.